Well, I hope everyone had a good Christmas, a happy new year. I'm recording this on the 1st of January. 1st of January, what better time than to do some physics? We're going to be doing Physics 3, the most common exam which was used, demonstrate understanding of mechanical systems. I think this is probably done by almost all level 3 physics students. I'm going to be using the level 3 resource paper that was given to you, and also the most common calculator that was used by New Zealand students. So, with any further ado, let's do it to it. First question is about momentum and circular motion. Titan is the largest of Saturn's moons. For the sake of this question, you can ignore gravitational effects from the other moons of Saturn. Okay, you could do that in real life, but let's go with it. The rest of the objects in the solar system, like the sun, you definitely couldn't do that, but let's do it. And assume that Titan is in a perfectly circular motion. Again, it's almost definitely not true, but let's go with it. Show that the center of mass between Saturn and Titan is 2.90 times 10 to the 5 meters, given all of these masses and distances here. Okay, well, the center of mass is always given as the mass 1 and the distance to a point plus mass 2 times the distance to that same point, and it's divided by m1 plus m2. Okay, so in this case, we're going to do a couple of things to make our life easier. If this is Saturn, that's the center of mass of Saturn, and that's Titan, and it's the center of mass of Titan. The center of mass is going to be somewhere along that line. Our origin point, our X point that we're going to measure distances from, I'm going to make it the center of mass of Saturn. And it's going to have be quite handy for us later on in algebraic terms. So the mass of Saturn, let's reset this mass of Saturn, and the distance. So that's going to be 5.68 times 10 to the 26th times now the distance between the center of mass of Saturn and the center of mass of Saturn is nothing, so they're going to cancel. That's why I took it from there. But the mass 2 of this thing, mass of Titan, is 1.35.23, not 0.23, times 10 to the 23 kilograms, and that's going to be multiplied to this distance here, which is 1.22 times 10 to the 9 meters. Okay, and then we need to add both of those masses together. So let's do Saturn first. 5.68 times 10 to the 26 plus 1.35 times 10 to the 23rd. Close it off. We've got everything we need, and we grab our calculator. So after we've ignored all of this bit, we get, in one bracket, 1.35 times 10 to the power of 23 times 1.22, 10 to the power of 9. That's upstairs. Divide that by downstairs now. 5.68 to the power of 26 plus 1.35 times 10 to the power of 23. Close that brackets, and we get this number here. So we get 28, and it's disappeared off my screen. 289,895.8874, and we need to convert that to 2.0, 2.90, and so 2.90 is definitely 5 decimal places times 10 to the 5. Yep, so that works. That would be our answer. And it doesn't matter whether you're finding the center of mass for a seesaw or your desk, the physics is still the same. Now we're told that 2 ice particles around Saturn move toward each other as shown below. So I guess here is particle B and particle A. Particle A, this one here, the red one, has a mass of 2.45 kilograms and a velocity of 8 meters per second. Particle B has a mass of 3.2 kilograms and a velocity of 15 meters per second. The particles collide and stick together, so it's perfectly inelastic. So inelastic, which means we need to use momentum in order to do it. You can lose kinetic energy in a perfectly inelastic collision. You can't make or destroy energy, but you can lose kinetic energy into a different form. Calculate the size and direction of the momentum of the two particles when they stick together. So momentum of A plus momentum of B must be the same as momentum of A plus the momentum of B. But notice that they're going at right angles to each other, so the angle is going to matter. So let's do let's do a momentum arrow for that. So here is A. So it's moving at a velocity of 8 meters per second. So it's in our SI units times 2.45. How much momentum is that? We need to grab our calculator. 45. 19.6. And the units for momentum, I think it's kilogram meters squared, something like that. But it's going in that direction. And now B is going to be going down in that direction, the momentum when it hits, and that is 15 meters per second times 3.2 kilograms. They're in SI unit. So the momentum of B is going to be 15 times 3.2, 48. 48. So let's do a little diagram that's a bit bigger than that. So the momentum for A here is going along there, and this is 19.6, and the momentum after they hit that B gives it to you is 48. So it's obviously not to scale, but it's a little bit more to scale than what I had. And the point where they have their intercept, both of them are going to join together, and they're going to go in that direction. Now we need to know what that theta is and what the magnitude is. So how are we going to do that? Well, the first thing we're going to do is we're going to note that this is a right angle triangle. So this side here, we'll call it A plus B. So A plus B squared is going to be equal to 19.6 squared plus 48 squared. And we grab our calculators for this. 19.6 squared plus 48 squared is 2688.16. But we know that A and A plus B together, let's put a little line on it to show that they're one line, is going to be the square root of that. So let's raise it to the power of 0.5, which is the same thing as taking the square root. 51.847. So 51.847 is how much momentum they're going to have. Second thing we need to know is how fast, what's the velocity that they're going to be doing? Well, the momentum A plus B is going to be equal to 51.847. But remember, that's a function of the mass of both of them times its velocity. So the mass of both of them is going to be, now one of them was, I think, 3.2 and 2.45. So it's perfectly inelastic times the velocity that they're moving. So 2.3, so 3.2, I'm gibbering a little bit, but those are the masses, both of them. So both of them combined form a mass of 5.65 kilograms. 65 kilograms times the velocity, and that's going to equal 51.847. So the velocity that they both move off at is going to be 51.847. 51.847 divided by 5.65. Okay. To the calculators we go. 51.847 divided by 5.65. 10.176. Sorry, 9.176. So they both move off at 9.176 meters per second. Now, what direction are they moving? And we need to find this theta angle. Well, theta angle, we're going to use tan. The opposite side is going to be 48. The adjacent side is going to be 19.6. So theta is going to be tan -1 of that. You're supposed to have the tan -1 over their side, but there you go. So tan -1 of that. And let's make sure that we've got this in degrees actually. So tan -1, 48 divided by 19.6. Is that in radians? Hang on. Yes, it was in radians, so let's do it again. So sine -1, 48 divided by 19.6 is, drum roll, 67.79. So there you go. After these two particles hit, they go along and they hit. One is going along like this. The other one is going on like this. They hit, they stick together, and they move off in that direction there at a rate of 9.176 meters per second. And this angle is 70, what did we say? 67.79 degrees. So we know everything we need to know about those two particles. Now the next question asks us to calculate the time it takes to complete one orbit of Saturn by Titan. And if you think about it, what we're actually looking for is t, the time period it takes to go around. You could begin by calculating the velocity of Titan in its orbit. So here I have all of the numbers and all of the formula that we will need to solve that. I've cut and pasted it. So first thing to remember is that Titan doesn't have any engines. It doesn't have rockets coming out of it that are propelling it around. And it's also in a circle. So the only force is the gravitational force. It must be equal to the centripetal force that it's exhibiting going around the circle. Now, let's set one to the other. Let's set FC equal to FG, because gravity is the only thing which is turning and spinning this moon around the planet. Okay, so once we've done that, we know that mv squared over r must be equal to g, big G, which is the gravitational constant. Big M must be the mass of Saturn, and little m must be the mass of Titan. I'm going to put a little t there so you can see that that's Titan and that's Saturn. Okay, this is all going to be over r squared, and this r squared is going to be the same. There's no t in there yet, but we can do that. Okay. What can we do to simplify things? Well, if we multiply both of these sides by r over 1, this r is going to go away, and we're going to lose an r there. We're going to lose the mass of Titan, and we're going to lose the mass of Titan there. They're going to cancel. So the velocity squared is going to be equal to the gravitational constant times the mass of Saturn divided by the radius of Saturn. So we're almost there. Almost there. We need t, but remember what velocity is. Velocity is distance over the time period it takes to get around there if you're going around in circles. So that's going to be equal to 2 pi r, r being the radius here, over the time period. That will be the velocity, and we would need to square that. Okay, so from here on in, it's algebra. So the algebra may or may not get messy, I don't know. So we have 2 pi r over t squared equals, if we square both sides, we took the yep, we can just bring this down because this is v squared is that, equals g m over r. Going down again, we want to break out this whatever's in this formula here. So 4 pi squared r squared over t squared is going to give us this. Okay, so now we want to expand that out. Yeah, I think we want to expand that out. So let's cross multiply. So 4 pi squared r cubed is going to be equal to gm t squared So therefore, the next question is an interesting question. Future manned missions to the solar system are most likely to be launched from space stations in low Earth orbit. Similar to the ISS, astronauts in the International Space Station appear to be weightless, even though Earth's gravity is still acting on them. Explain why astronauts appear to be weightless yet can remain in orbit. Well, when you're in orbit, you're going across the surface of the Earth in that direction. And the Earth is kind of going, sort of curving away from you. But you are also falling towards Earth, and the falling towards Earth pulls you around. And as long as you are going that way at the same rate that you're being pulled towards Earth, and the Earth is sort of forever curving down away from you, you're technically in an orbit. That's what orbit is. You're falling towards the Earth, but the Earth is kind of falling away from you in a way. You have to be moving sideways across the Earth and in line with gravity. It's a little bit tricky to get in there, but as long as that's happening, then you will be apparently weightless. Okay. You'll still have the same mass, but because everything is falling at the same rate, it will appear that gravity is not working. Well, isn't there. So you will appear weightless. You're in what's called microgravity, which means you're still being pulled by the Earth, but you're also moving sideways. And the sideways means that the Earth is always tilting away from you at the same rate that you're going forward, and you're getting pulled around that curve. It's a little bit like Newton's cannon. He said if you fire a cannonball, it'll sort of land there. If you fire a more powerful cannonball across the surface, it'll go there, but it'll also get pulled and maybe land there. But if you land one fast enough, it'll have enough energy to move out and into orbit. So it's always being pulled into the middle of the center of gravity of the Earth, but it's also going that way. And those two forces combine mean that it is orbiting now the Earth. So that's why it appears that you float, just because everything else is falling with you. It's a little bit like being in an elevator and you cut the cord. Everything suddenly is going to be weightless because everything is going to be falling at the same rate. So your can of Coke here is the contents are going to pull out, are going to sort of come out. And just like that, we're at rotational motion. So Rahari and Jane playing on a roundabout, good for them. And the local playground, good for them. A roundabout has a radius of 1.3 meters. Okay, so that's worth noting, 1.3 meters. Rahari stands on the roundabout while Jane pushes. Oh, pull your weight, Rahari, on it to make it spin, shown in the diagram. Starting from rest, Jane steadily accelerates the roundabout so that it takes 12 seconds to make 4 rotations. Show the angular velocity of the roundabout after the 12 seconds is 4.19 radians. Okay, we can use this formula. The radial distance is the initial angular velocity plus the final angular velocity over 2 times time. You'll see a lot similar. Distance is VI plus VF over 2 times T. You would have seen that last year. Same concept here, whereas this is going to be in radians. So VI, it starts from a stop. So VI, I'm sort of VI, omega I is 0. Omega F, well, we don't know if it's 4.9, but we need to prove it. The time is 12 seconds, and the amount that it's gone around is 4 notations. One rotation is 2 pi, so 4 rotations is 8 pi. So now it's an algebra question. So 8 pi is going to be equal to the final angular velocity divided by 2 times 12. And that final VF, we hope it's 4.9. So let's check. Yes, we're on radians. Let's exit out of there. So I guess we could say 16 pi equals 12 VF. So omega final is going to be 16 pi divided by 12. And it's going to give us a nicer number. So 16 pi divided by 12 equals 4.188. 4.1887, which is 4.19 radians, 3 significant figures. Okay, for this one, we're told that Rahari now drags his foot along the ground to bring the roundabout to a stop over 19.2 seconds, presumably from this 4.19 radians second. So calculate the average torque exerted to slow the roundabout if the roundabout and Rahari have a rotational inertia of 430 kilogram meter squared. Well, we know that subtributive acceleration is change in circular motion over the time it took to get there. And we know that that's going to be negative 4.19 because it's gone from 4.19 to 0. And we know that that took 19.2 seconds. So that's going to be 4.19 divided by 19.2 seconds. That number there, 0.2182, negative 82 radians per second, negative radians per second. And we know that pi is that inertial rotation times the acceleration. So that's going to be 430 times that minus 0.2182. And let's do that, times 430, negative 93.84 newtons, and the negative means it's a slowing force, because you still have to do work to slow something down if it's already moving. Okay, and I think that's it. I think it's as complicated as that way gets. So for this question, Jane now takes a run at the roundabout, jumps onto it, and she is 52 kilograms. That's her mass. She's running at 6.39 meters per second, and she jumps onto the roundabout, I guess, and it takes her energy and her momentum close to the edge, landing 1.2 meters from the axis of rotation. The roundabout in Rahari, who's this person here, is already on there, and it already has 430 kilogram meters squared, and the rotation of mass is going to be that's what's already on there. So, looking at Jane here, we need to work out how much angular momentum she puts into this roundabout and how much it's going to spin as a result. This is actually a perfectly inelastic collision. So if you try to use energy equations, you would probably come a cropper. Much better to use momentum. All right, so the angular momentum that Jane imparts onto this is going to be, I'm going to need to look at the formulae. The angular that Jane puts into it is going to be mvr, and it's going to be her mass, 52 kilograms, times her velocity, which is 6.39 meters per second, times the radius from the end, and it tells us that this is 1.2 meters, i.e. the amount of torque that she's going to put into this roundabout. And that's going to come to some number. So let's grab our calculator and work it out. So 52 times 6.39 meters per second times 1.2 meters away from the center of mass, 395.736. So 398.736 amount of momentum. So now we need to work out the total rotation of this roundabout now that she's on there. So this is going to be equal to, what did they say? 430 kilogram meter squared plus, and now we have Jane. So Jane is also now a member of the system, times 1.2, this one here, squared. So this is going to be some other number. So 430, that's what's already on there, plus 52 times 1.2 squared is that. So we're going to get 504.88 is the moment of inertia for this whole roundabout now that Jane and what's his face Rahari are both on there. Okay, well, we know that Li is going to be equal to the total inertia times the rotational angular velocity, which is what we've got there. So we've got that. Now we need to find this. So the angular velocity is going to be equal to this amount of momentum that was given into the system by Jane over this total inertia, this 504.88, and that's kind of, think of that as the mass. So that's going to be 398.736 divided by 504.88. And the good thing is that now we're using SI units. The result that we get back will be in radians, divided by 504.88 0.88. So 0.7877898 radians per second. And that's our answer. So, yeah, knowing what these L's and I's, what they actually mean, and the fact that once she joins, you can't use energy considerations because it's an inelastic collision, and that's the answer there. Now we're told that later Rahari and Jane are both standing on the edge of the roundabout while it is rotating at a constant angular velocity. Rahari moves inwards towards the centre of the roundabout. Explain the effect this has on the rotational energy of the system. Well, this relates to the conservation of momentum and energy. Okay, so the angular momentum must be maintained. So L final must be L initial, and that's going to be equal to I times the constant times the amount of rotation that you have. In this case, the kinetic energy in the system will increase. So EKROT will increase. And you may be asking yourself, well, where does that energy come from? Well, it comes from chemical potential energy in the legs of this person. Is there the worst legs in the world, worst drawing of legs in the world? Maybe that's, that's their other leg. They walk towards the middle. The chemical potential energy means that she does work by lowering the moment of inertia of the roundabout. And because, momentum and energy have to be conserved, it gets, I'm saying this really badly, it gets turned into rotational kinetic energy. So chemical potential energy becomes actual kinetic energy, which becomes rotational kinetic energy, and the conservation of momentum must be held constant at all costs. So let's see how she does this. The moment of inertia of the system is mr squared. Now, if r is going down and the change of the mass is nothing, then r going down a little bit because it's squared, the moment of inertia must go down a lot. So it's a little bit like the spinning skating dancer. When she raises her hands in the air and makes everything close to the center of rotation, she'll spin faster because now she has a smaller moment of rotation. Okay, so because L must be conserved, and that's angular momentum, then something has to give. So if L stays the same, and that's equal to I W, and we know that has gone down, that there is no change in that, then this must increase. And because kinetic energy from rotation is half I W squared, and I has gone down and omega has to go up. If omega goes up, 1, because it's squared, the kinetic energy of rotation must go up a lot. So momentum is conserved, mass is conserved, energy is still conserved, but it's converted from chemical energy to linear kinetic energy to rotational kinetic energy in this case? It's a nice question. So let's do a little bit of a thing there. So chemical potential energy in her legs is transferred to kinetic energy in her feet, which is converted to a couple of things. The moment of inertia must go down. The distance to the center must go down. The the angular velocity must go up, and the kinetic energy from rotation must go up as well. So a little change in that makes a lot of difference. A lot of engineering, if you look at old machines, they will have bits sticking at the top, and there will be like a ball on this side and a ball on this side, and this whole thing sort of spins around. The reason they're doing that is it's a type of flywheel. It's so that they keep momentum, and they don't lose energy while they're making something. If you go to particularly the UK, you'll see a lot of engines with these two little balls sticking out on a stick that spin. That's why they do it. It's a type of flywheel, and it exploits this phenomenon. A really good question. Really good question. Okay, we have a good old pendulum simple harmonic motion question now. Rahari is playing with a ball on a string, lets it swing as pendulum. It is 1.2 meters from a fixed point of the string to the center of mass of the ball. The top of the string is held, and the ball is released from a starting position at an angle of 5.6 degrees. Ooh, I don't like that. Degrees from the vertical. The mass of the string is insignificant. Okay, so we can ignore the mass of the string compared to the mass of the ball. Show that the maximum displacement of the ball is that much. So the displacement is pretty much this distance here. Okay. Now, how do we do that? First thing we need to do, I guess, is we need to compare like with like. So this is already in SI units, but this angle is not in SI units. So remember, it's 5/6 out of the 360 degrees is going to be equal to whatever it is in radians divided by 2 pi radians, which means that the displacement is in radians. The displacement radians is going to be, how are we going to do this? 5.6 times 2 pi over 360. So let's have a look. 5.6, be better if you could see it, times 2 times pi is that. Divide that by 360. So that's 0.0977 radians. So the R is, well, theta is equal to 0.0977 4 radians. Should be enough. And we know that the distance arced out is the length of the radius times that, and it has to be in degrees. So it's 1.2 times this number here, and that will give us the displacement. And sure enough, that is 0.117 to 8 of that number there, which is this back 0.117 meters. This one isn't quite so easy. We're going to have to do a bit of algebra. So I'm going to use these three formulae that are given down the bottom because they're not looking for F. You might see that word frequency, but we want angular frequency. We're actually looking for this omega. Okay, first thing we do before we do any of this stuff is we're going to combine these two formula. So omega is 2 pi frequency, and frequency is 1 over t. So it follows from that t must be 1 over f, but we won't worry about that for now. Wherever we see an f, we're going to put this 1 over t in its place. So this omega here is going to be equal to 2 pi over big T. Okay, so we've got that. But we know that the 2t here is equal to this. That t is equal to this. Okay, so this is going to be equal to 2 pi divided by 2 pi L over G, where G is the 9.81 and L is the length of the rope, which is 1.2. Rope of the string, length of the string, which is 1.2. Now, if you notice, those are going to cancel. So the angular momentum is going to be 1 over the square root L over G. Okay, so now when we put those numbers in, we should get the answer that we're looking for. So 1 divided by, and let's on the square root button, square root brackets 1.2 divided by 9.81. No, not 9.981. 9.81. Close brackets there. Close brackets there. And we get 2.859. Okay. 2.859, which is 2.86 to 3 significant figures, and that would be our answer. So yeah, don't confuse angular velocity and frequency with linear frequency. They're not the same thing, and a lot of students probably did fall for that little trap, but that's the trick there. So the next question is a reference circle question. So after the ball is released from the starting position, which we presume is at that maximum level there, calculate the time it will take for the ball to reach a point 3.3 centimeters before its next stationary position, as shown on the diagram being the one above. A reference circle may be used to calculate the answer. So I've done one step further than that, and I've done a complete one on HTML, and in a second I'll bring it up. So here is a little program. It's quite a long program. I might put it on the website. It has exactly the same things that we had there before. So when I play it, this thing goes from left to right and around and back and around and back. So that is what they're sort of looking for. Yeah, the displacement is shown here. I think I'm going to. Okay, let's do the algebra then. We know from the notes, from the formula given, that y equals a cos omega t, and we could use any of them, but they're all in the same format. A is the amplitude. We've already been given the amplitude at 0.117 meters, and it's already in SI units. So at time t equals 0, we know that y, which is just the displacement, is going to be 0.033. It's 3.3 centimeters, I think they gave it to us. We have to have it in meters. The next stationary point is on the other side of the circle, where the amplitude is at -1. That's the other side. Okay, so yt, the one that we're looking for, is going to be at 0.033 minus amplitude, which is going to be 0.033 minus 0.117. And I worked this one out beforehand, and that's going to be at minus 0.84. And the minus just means it's once it's gone around the circle on the other side. So for this side here, we know that the amplitude there is on the other side is going to be that negative. So negative 0.084 is going to be equal to the amplitude. So this negative 0.44 is where it's going to be the next time that it meets that criteria, the next stationary point. Okay, that's why it's a negative number. And that's going to be cosine. Now, omega is a little bit tough. Omega, we kind of need to work out. Or do we? Well, the answer is no, we don't, because we already worked it out. So 2.86 times time. And we want to solve for time. So let's do everything sort of above board. So cos 2.86t, and we're going to divide both sides over, must be equal to 0.084 divided by the 0.117. So you see what I did here? I flipped sides and I brought this one over. Okay, so far so good. And I'm going to even simplify that as negative 0.7179. So cos, let's get rid of the cos. So 2.86t is going to be equal to cos -1 of that number. Okay. And that gets, on my calculator that I've got here, that comes to 2.371. So therefore t must be that number divided by 2.86 if they're going to cancel. And it gives us the final answer of 0.8295. And they're all in meters and they're all in radians. So that has to be in seconds. Again, this is an extended question. So I'm going to presume that you know what it did there with the algebra. And I'll put the code there if you want it. Right, the last question says that Rihari holds the end of the string between his fingers, moves his hand horizontally from side to side, and he notices at a certain frequency of movement the ball will oscillate with a very large amplitude. Explains why this happens. You should include both force and energy. Okay, so let's do force first. So he's imparting a forced oscillation into the system. Okay, so it's often called a driven oscillation. What that does, it interacts. Oh, what happened there? Of the pendulum system through constructive and destructive interference. When the driven movement is constructive and the resonant frequency is constructive, we have a node in which we have large amplitude, and vice versa. So destructive and constructive can meet, and we can have a small one. The energy is being transferred from his hand. So it's from chemical potential energy to kinetic. I hope you could read that. Okay. So in resonance, the energy from his hand transfers most easily. So he hasn't changed the resonance of the system. He's just trying to impart forced oscillations, and that will interact with how the pendulum wants to go. And when the forced oscillations match the resonant oscillations, you get a big amplitude, and when they are antinode to each other, you'll get a much reduced. So it's going to sort of go little, big, little, big, little, in that sort of format. It's not going to go big, little, big, little. Okay, and that's the end of the exam. It's a pretty reasonable exam. Lots of algebra, but there weren't really many questions that didn't require you to use the formula that were given. So all in all, a pretty good exam.